The universe is a place of unimaginable extremes where temperatures soar so high they could vaporize entire planets in seconds, and plunge so low they defy everything we know about cold. Right now, somewhere out there, a star is burning hotter than 15 million degrees Celsius at its core, while the empty void between galaxies lingers just above absolute zero. But what if I told you these are just the beginning? From searing stellar furnaces to icy cosmic deserts, today we're uncovering 50 astonishing facts about the universe's most extreme temperatures, places where the rules of physics seem to bend, and reality itself becomes stranger than fiction. Buckle up, because some of these numbers will leave you questioning everything you thought you knew about hot and cold. At the heart of our solar system, the Sun burns with a ferocity beyond human comprehension, its core reaching a blistering 15 million degrees Celsius. That's more than 27 million degrees Fahrenheit, a temperature so extreme it rips atoms apart, forging new elements in a relentless nuclear fusion reaction. Every second, 600 million tons of hydrogen slam together, transforming into helium and unleashing enough energy to power our entire solar system for millennia. To put that into perspective, Earth's hottest recorded temperature, a mere 56.7 degrees Celsius in Death Valley, would barely register as a chilly breeze against the Sun's unimaginable heat. Without this cosmic furnace churning away, life as we know it wouldn't exist. The sheer scale of its energy output is humbling, yet it's just one of countless stars burning even hotter across the universe. But the Sun's core isn't the only place where temperatures reach mind-bending extremes. When solar flares erupt from its surface, they unleash storms of plasma heated to between 10 and 20 million degrees Celsius hotter than the Sun's own core. These twisting ribbons of fire stretch hundreds of thousands of kilometers into space, catapulting charged particles at nearly the speed of light. A single flare can release the energy of 1 billion hydrogen bombs in mere minutes. While mesmerizing to observe, these eruptions aren't just cosmic fireworks. They create space weather capable of crippling satellites, disrupting radio communications, and even causing massive power outages on Earth. In 1989, a solar storm plunged 6 million people into darkness across Quebec when it overloaded electrical grids. Just last year, a flare narrowly missed Earth but would have knocked out global positioning systems for days. It's a dramatic reminder that even from 93 million miles away, our star's searing tantrums can reach out and touch us. While the Sun's fury dominates our solar system, Venus holds its own terrifying temperature record. This world is home to lightning bolts that burn hotter than its already scorching surface. Picture a planet where temperatures average 465 degrees Celsius, hot enough to melt lead. Yet somehow, in the thick clouds of sulfuric acid swirling above, electrical discharges ignite that are even more intense. These aren't your typical thunderstorms, Venusian lightning strikes with temperatures reaching an astonishing 30,000 degrees Celsius, 5 times hotter than the planet's already infernal surface. The thick, toxic atmosphere traps heat like a runaway greenhouse, while charged particles collide in those acid-laden clouds, unleashing bolts of pure energy with terrifying unpredictability. NASA Pioneer Venus Orbiter first confirmed these strikes in the 1970s, and since then, we've learned they're far more frequent than Earth's lightning. Just another reminder that Venus isn't just hellishly hot, it's electrically charged chaos. Mercury plays host to one of the most brutal temperature swings in the solar system, a world where the difference between day and night feels less like a change of weather and more like leaping between two entirely different planets. Under the Sun's unrelenting glare, surface temperatures soar past 430 degrees Celsius, hot enough to melt zinc. Yet when night falls, the thermometer plummets to a bone-chilling -180 degrees, colder than Earth's most frigid polar winters. This wild swing isn't just extreme, it's downright violent, and Mercury's paper-thin atmosphere is to blame. Unlike Earth, which has a thick blanket of air to trap and distribute heat, Mercury's wispy exosphere is barely there at all. With nothing to hold warmth, the moment sunlight vanishes, heat escapes into space at breakneck speed. Picture baking a stone in an oven, then tossing it into a freezer. That's Mercury's daily routine. Even more astonishing, some craters near its poles never see sunlight at all, harboring shadowy ice pockets in a world where nearby planes could fry electronics in seconds. It's a planet of contradictions where fire and ice exist side by side, separated only by the turning of a sunlit hour. Jupiter's moon Io is a world on fire, literally. While most moons are frozen wastelands, this chaotic little orb boasts the most explosive volcanic activity in the entire solar system. Its lakes of molten rock rage at a staggering 1,300 degrees Celsius, hotter than any lava flow Earth has ever produced. But here's the twist: Io isn't powered by a fiery core like our planet. Instead, it's the gravitational tug of war between Jupiter and neighboring moons that kneads its insides like dough, creating enough friction to melt rock from within. The result: hundreds of active sulfur-spewing volcanoes, some blasting plumes 500 kilometers high, taller than the distance from Earth's surface to the International Space Station. Picture Mount St. Helens, then multiply its fury by 100, and you're still not close to the spectacle on Io. Rivers of liquid sulfur cascade across its surface, painting the moon in surreal yellows and oranges, while volcanic calderas larger than cities churn with magma. It's a place where geology becomes extreme sport, and the very ground beneath your feet could erupt without warning. NASA Juno spacecraft recently captured infrared images showing clusters of these eruptions glowing like a cosmic bonfire. Proof that even after decades of observation, Io refuses to cool down. Beyond our solar system, there's a world so scorching it defies sanity: Kelt 9b, an exoplanet where temperatures shatter every record. This infernal planet orbits its star so closely that a single year lasts just 1.5 Earth days, and its day side blazes at an unimaginable 4,300 degrees Celsius. That's hotter than the surface of some stars, including red dwarfs. Imagine a place where metals like titanium and iron don't just melt, they vaporize into swirling gases. Kelt 9b's host star bombards it with ultraviolet radiation so intense that the planet's atmosphere is literally boiling away, trailing a comet-like tail of vaporized heavy metals. Scientists believe it's losing around 10 billion tons of material every second, a slow cosmic demolition. The star's gravitational grip locks one side of the planet in perpetual daylight, turning it into a permanent furnace, while the night side, though slightly cooler, still roasts at temperatures that would liquefy rock. Even stranger, Kelt 9b's orbit is flipped backward compared to its star's rotation, a cosmic oddity suggesting a violent past, possibly a collision or near miss with another massive object. This isn't just a planet, it's a glimpse into how extreme the universe can get when the rules of physics are pushed to their limits. In the violent aftermath of a supernova, something extraordinary emerges: a neutron star, one of the universe's most extreme survivors. Fresh from the cosmic furnace, these newborn stellar corpses blaze at over 1 million degrees Celsius on their surfaces, radiating heat so intense it could vaporize any known material in an instant. But the real shocker, that searing temperature is just the tip of the iceberg, packing more mass than our Sun into a sphere barely 20 kilometers wide. Neutron stars are so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. Their surfaces are forged in the cataclysm of a supernova explosion, where atoms get crushed so violently that electrons and protons merge into neutrons, unleashing a storm of energy that superheats the star's outer layers. And if the heat wasn't enough, their magnetic fields are another nightmare, trillions of times stronger than Earth's. twisting the very fabric of space around them. These fields act like cosmic blowtorches, channeling plasma into fiery jets that shoot from the poles at nearly light speed. Imagine a magnet so powerful it could strip the iron from your blood from thousands of light years away. That's the terrifying reality of a neutron star's birth. Even decades after their creation, their surfaces still glow with the echoes of that initial inferno, a reminder of the universe's capacity for both destruction and breathtaking rebirth. When a massive star reaches the end of its life, it doesn't fade quietly. It goes out with a bang so colossal it reshapes the fabric of space itself. Supernovas are nature's ultimate explosions, and within their shockwaves, temperatures spike to an almost incomprehensible 100 billion degrees Celsius. That's 60 times hotter than the core of our Sun, a fleeting but unimaginable inferno where matter itself gets rewritten. In these brief, cataclysmic moments, atomic nuclei, crushed together at unimaginable speeds, forge elements heavier than iron, the very building blocks of planets and life. Gold in your jewelry, uranium in reactors, even the calcium in your bones, they were all born in the heart of these dying stars, blasted into space by forces beyond human scale. The shockwave alone travels at 30,000 kilometers per second, ripping through the star's outer layers like tissue paper, and in its wake, a swirling cauldron of neutron-rich material where particles collide with such violence that protons and electrons merge, creating rare heavy elements in a process called rapid neutron capture. For context, the heat here is so extreme that even atoms can't hold their structure. They're torn apart into a seething plasma of quarks and gluons, the universe's most fundamental particles. What's left behind isn't just destruction but creation, a nebula glittering with newly forged stardust, the raw material for future stars, planets, and perhaps even life. Yet these explosions aren't just cosmic foundries, they're also laboratories for extremes we can't replicate on Earth. Scientists study them to understand how matter behaves under such insane conditions, unlocking secrets about the origins of everything around us. The next time you hold a piece of metal, remember, it might have once raced through space at near light speed, forged in a fire so hot it defies imagination. Deep in the hearts of distant galaxies, quasars blaze with a brilliance that dwarfs entire star clusters, cosmic beacons powered by supermassive black holes feasting on matter at impossible scales. These aren't just hungry voids, they're surrounded by swirling maelstroms of superheated gas called accretion disks, where temperatures spiral into the trillions of degrees Celsius. That's hundreds of times hotter than the core of a supernova, a thermal frenzy so intense it warps the very laws of physics we know. Picture a ring of plasma spinning near light speed, compressed and heated until atoms surrender entirely, dissolving into raw energy. The friction alone within these disks generates enough heat to outshine 1,000 galaxies, lighting up the cosmos like a lighthouse piercing through fog. Much of that energy comes from matter crossing the event horizon, but the real spectacle happens just outside, where particles collide with such violence that they emit X-rays and gamma rays detectable across the universe. Yet quasars aren't just cosmic blowtorches, they're galactic architects. Their ferocious energy output can sterilize entire star systems, but paradoxically, they also trigger star formation in distant gas clouds, sculpting galaxies over billions of years. Some scientists believe these ancient monsters even helped reionize the early universe, tearing apart the fog of primordial hydrogen to make space transparent to light. We're seeing them now as they were eons ago, their light only just reaching us, glimpses of an era when black holes ruled as the universe's most formidable engines of creation and destruction. What's truly humbling, the brightest quasar ever discovered, J0430+1634, emits enough energy every second to power human civilization for 100 trillion years. And somewhere, right now, another one is waking up, its heat rewriting the rules of its corner of the cosmos, proving once again that the universe prefers its extremes dialed all the way up. While the universe today blazes with stars and quasars, there's a hidden chill lingering from its very birth, a cosmic echo called the cosmic microwave background. This faint glow blankets the entire universe at a frigid -270.4 degrees Celsius, just a few degrees above absolute zero. It's the oldest light we can detect, a snapshot of the cosmos when it was a mere 380,000 years old, long before stars or galaxies existed. Back then, the universe was a seething plasma too hot for atoms to form, until expansion cooled it just enough for light to break free. That first burst of radiation has been stretching and cooling ever since, fading into microwaves over 13 billion years. Scientists call it the universe's baby picture, and mapping its subtle temperature fluctuations reveals something extraordinary, the seeds of everything we see today. Those tiny variations, some as small as 1 part in 100,000, mark where matter began clumping together, destined to become galaxies and superclusters. Satellites like Planck and WMAP have charted this ancient light with stunning precision, showing a mottled tapestry of warmer blues and cooler reds, the universe's original blueprint. What's truly mind-bending, we're swimming in this radiation right now. Your old analog TV static, about 1% of that snowy interference came from the Big Bang's afterglow. It's a humbling thought. Every direction we look, we're glimpsing the universe's fiery infancy, cooled to a whisper but still whispering its story across the void. Absolute zero isn't just cold, it's the ultimate limit of temperature, the point where even atoms give up shivering. At -273.15 degrees Celsius, all molecular motion theoretically stops completely. But here's the catch: reaching this mythical temperature is impossible, no matter how advanced our technology becomes. Quantum mechanics ensures that particles always retain a faint whisper of movement, a fundamental property called zero-point energy. Even in the emptiest, coldest regions of space, where temperatures hover just a degree above absolute zero, nature refuses to hit pause. Scientists have come breathtakingly close. MIT researchers once chilled sodium gas to within 0.5 billionth of a degree above absolute zero using lasers and magnetic traps. At these extremes, matter starts behaving in surreal ways. Atoms lose their individualism, merging into a strange quantum soup called a Bose-Einstein condensate where thousands of particles move in eerie unison. Yet that final sliver of warmth stubbornly lingers, a cosmic speed bump dictated by the very laws of reality. This isn't just lab curiosity. Understanding these limits reshapes technology. Superconductors, quantum computers, and even ultra-precise atomic clocks all rely on pushing temperatures to these extremes. The universe seems to whisper a lesson in every experiment. Perfection might be unreachable, but the pursuit reveals wonders we never imagined. Out in the vast emptiness of space, the Boomerang Nebula holds a record that would make even Antarctica shiver. This cosmic ghost is the coldest known place in the universe, a frigid -272 degrees Celsius. That's just 1 degree above absolute zero, colder than the darkest shadows of Pluto or the void between galaxies. So how does a nebula, typically a place of stellar birth and fiery death, become a freezer of cosmic proportions? The answer lies in its violent past. This nebula isn't just drifting. It's racing outward at nearly 160,000 kilometers per hour. Its gas expanding so rapidly that it chills itself in the process, like a cosmic air conditioner set to maximum. To grasp just how cold that is, consider this. The coldest temperature ever recorded on Earth was -98 degrees Celsius in Antarctica, a bitter snap that could freeze your breath in midair. Yet even that's practically tropical compared to the Boomerang's deep freeze. Here, molecules slow to a crawl, light dims to a whisper, and the very fabric of heat seems to unravel. What's even more astonishing, this nebula wasn't always icy. It's the death shroud of an ancient red giant star, which in its final throes ejected its outer layers in a desperate, hyper-fast outflow. That rapid expansion sucked away the energy, leaving behind a ghostly haze colder than the afterglow of the Big Bang itself. Hubble's images reveal its delicate bow tie shape, not from heat but from absence, a void where motion nearly stops. Scientists study it like a cosmic laboratory, probing how matter behaves when pushed to the brink of stillness. And somewhere out there, another star might be preparing for the same eerie fate, ready to turn its dying breath into the universe's next deep freeze. Pluto's heart isn't just iconic, it's a frozen marvel where nitrogen glaciers flow across a landscape colder than imagination. The dwarf planet's surface hovers around -240 degrees Celsius, so frigid that even its thin atmosphere occasionally freezes and falls like snow. But the real spectacle lies in Sputnik Planitia, that vast, heart-shaped plain captured in stunning detail by NASA, a New Horizons mission. Unlike Earth's rocky glaciers, this Texas-sized basin is packed with soft, flowing nitrogen ice, slushy enough to creep forward like slow-motion putty, reshaping Pluto's terrain over millennia. The New Horizons images reveal a fractured mosaic of polygonal cells, each spanning kilometers, where heat from Pluto's interior bubbles up like a cosmic lava lamp. Only here, the lava is frozen nitrogen contorting under pressure. Towering ice mountains loom at the edges, their water ice peaks too rigid to flow, standing sentinel over the surreal, shifting plains below. What makes this even wilder? Pluto's tilted orbit creates seasons so extreme that its atmosphere balloons and collapses like a cosmic lung, sometimes thick enough to allow winds to sculpt the ice, other times vanishing almost entirely as gases freeze solid. This isn't just a dead world. It's a dynamic, icy laboratory where exotic ices of nitrogen, methane, and carbon monoxide dance between solid and gas, defying our Earth-centric ideas of geology. Every crack and ridge in Sputnik Planitia whispers secrets about how small, distant worlds stay geologically alive. No molten core required. And somewhere beneath that glacier, scientists suspect a subsurface ocean might lurk, kept liquid by radioactive decay and the insulating grip of all that ice. Pluto's heart isn't frozen in time, it's beating to the rhythm of the cosmos itself. Beneath Europa's cracked, frozen shell lies one of the solar system's greatest mysteries, a vast ocean of liquid water, hidden under ice as cold as -160 degrees Celsius. This isn't some shallow pocket of slush. Scientists estimate it could hold twice the volume of all Earth's oceans combined, locked beneath an icy crust up to 24 kilometers thick. So how does water stay liquid in such a frozen wasteland? The answer lies in Jupiter's relentless gravitational pull. As Europa orbits, the gas giant's immense gravity stretches and squeezes the moon, generating internal friction through tidal forces. This constant flexing produces enough heat to melt ice deep below the surface, creating a global salty ocean that never freezes solid. What makes this discovery so electrifying isn't just the water, it's what might be swimming in it. Hydrothermal vents on Earth's ocean floors teem with life, thriving without sunlight in extreme pressure and heat. Europa's dark depths could harbor similar ecosystems, where microbes or even complex organisms might cling to energy from chemical reactions rather than sunlight. NASA's upcoming Europa Clipper mission aims to scan the ice shell for plumes erupting from below, potentially offering our first direct samples of this alien ocean. Imagine if just one of those icy geysers carries microscopic proof that we're not alone in the universe. This moon challenges everything we thought we knew about where life can exist. A world where sunlight never penetrates, where surface temperatures could shatter steel, might ironically be one of the most promising places to find neighbors in the cosmos. As we peer into Europa's frozen cracks, we're not just studying a moon, we're staring into a mirror, reflecting the tantalizing possibility that life is far more adaptable and far more widespread than we ever dared to dream. While Mars might look like a dusty desert world, its poles tell a far colder story, a frozen wasteland where temperatures plunge to -125 degrees Celsius, cold enough to turn carbon dioxide straight into dry ice. Unlike Earth's polar caps made of water ice, Mars' poles are layered with vast sheets of frozen CO2, creating surreal landscapes of frost that expand and retreat with the seasons. During winter, nearly a third of the planet's entire atmosphere freezes out onto these caps, building layers of dry ice so thick they can be spotted from orbit. Then, when spring arrives, the ice sublimates back into gas, triggering bizarre geysers that spew dust and vapor hundreds of feet into the thin Martian air. NASA rovers have uncovered even stranger details like the Phoenix lander, which scraped beneath the surface near the North Pole and found water ice hiding just below the dry ice blanket. It's a frozen lasagna of alien geology, layers of CO2 frost, water ice, and wind-blown dust stacked over millennia. These polar regions aren't just static ice caps, they're dynamic, breathing landscapes that shape Mars' climate. Satellite images reveal spider-like cracks radiating across the ice, carved by escaping gas, while towering dunes of frozen CO2 shift like slow-motion waves. The chilling reality: Mars' poles are colder than Antarctica's deepest freeze, yet they hold clues to the planet's wetter past, and perhaps even secrets about how volatile substances dance between solid and gas on other worlds. Every layer of ice is a time capsule, waiting to reveal how Mars transformed from a planet with rivers to the frozen frontier we see today. Saturn's moon Titan doesn't just defy expectations, it rewrites them entirely. While most moons are barren rocks or frozen ice balls, Titan boasts something extraordinary: vast lakes and rivers of liquid methane, shimmering under a hazy orange sky at a bone-chilling -180 degrees Celsius. This isn't science fiction, it's the only place in the solar system, other than Earth, with stable liquid flowing across its surface. Picture a world where rain falls not as water, but as liquid methane, carving valleys and pooling into lakes the size of the Great Lakes on Earth. The Cassini spacecraft revealed this alien hydrology in stunning detail. Dark, smooth patches near Titan's poles turned out to be methane seas like Kraken Mare, stretching over 400 kilometers wide. But here's the twist: Titan's methane cycle mirrors Earth's water cycle with eerie precision. Evaporation forms methane clouds, storms dump methane rain, and rivers of it carve intricate networks into icy bedrock. Even the shorelines show signs of tides and waves, driven not by the moon but by Saturn's immense gravity. What makes this even wilder: beneath Titan's icy crust may lie an ocean of water and ammonia, meaning this moon has two entirely separate liquid cycles, one on the surface, one below, each operating under conditions that would be impossible on Earth. Scientists suspect Titan's chemistry could even hint at how life might arise in environments we once thought too extreme. Every droplet of methane rain, every ripple on those alien lakes, forces us to rethink what's possible in the cosmos. One thing's certain: Titan isn't just a moon, it's a looking glass showing us a world where the familiar becomes profoundly strange. Uranus takes cold to an entirely new level. Its atmosphere holds the record for the chilliest planetary environment in our solar system, a teeth-chattering -224 degrees Celsius. That's so cold even nitrogen, which makes up most of Earth's air, would freeze solid and drop like snow. But the real kicker: Uranus doesn't just endure this deep freeze, it does so while lying practically on its side. Unlike other planets that spin like tops, this ice giant rolls around the sun like a cosmic bowling ball, its axis tilted a jaw-dropping 98 degrees. This bizarre tilt creates seasons more extreme than anywhere else in our solar neighborhood. For roughly 21 Earth years at a time, one pole of Uranus faces the sun non-stop, while the other plunges into endless darkness. Imagine a winter so relentless it lasts decades, then flip it to a summer just as long, with the sun circling overhead like a tireless spotlight. The result: wild temperature swings in the upper atmosphere, where methane clouds swirl in a sluggish dance, and winds still manage to howl at 900 kilometers per hour despite the bitter cold. Yet the mysteries don't stop there. Voyager 2's flyby in 1986 revealed a planet oddly lacking internal heat, unlike its sibling Neptune. Scientists are still debating whether a colossal impact knocked Uranus sideways and drained its warmth, or if its interior simply cooled in some unique way. What's certain is this: Uranus isn't just another icy world, it's a lesson in how planets can defy expectations, turning what we know about seasons, heat, and even planetary formation on its head. Not all cosmic cold spots belong to planets. Some lurk in the realm of failed stars. Meet WISE 0855, the coldest known brown dwarf, chilling at a frosty -23 degrees Celsius. That's colder than a winter night in Siberia, yet this object isn't a planet at all. Brown dwarfs are cosmic misfits, too massive to be planets, but too small to ignite full nuclear fusion like stars. WISE 0855 is an infrared ghost emitting barely any visible light, only spotted by NASA, a heat-seeking WISE telescope after years of painstaking analysis. What makes this dim object so fascinating? Its temperature is startlingly close to Jupiter's, hovering just a few degrees cooler than the gas giant's cloud tops. But while Jupiter basks in the sun's warmth, this brown dwarf drifts alone in interstellar space, 7 light-years away, radiating only the faintest heat from its slow gravitational collapse. Picture a world where the sunset never ends, a perpetual twilight with no star to warm it, no day or night, just an eternal, icy gloom. Yet even in this deep freeze, WISE 0855 holds surprises. Its atmosphere swirls with water ice clouds, the first ever detected outside our solar system, proof that the ingredients of familiar weather can exist in the most isolated corners of the galaxy. Astronomers compare its spectrum to Jupiter's, searching for clues about how planetary atmospheres behave in extreme cold. This cosmic loner challenges our definitions, blurring the line between planet and star, reminding us that the universe loves to defy categories. While nature pushes temperature extremes across the cosmos, human ingenuity has crafted its own record-breaking chill, inside laboratories where scientists bend the rules of physics. At MIT, researchers performed an astonishing feat by cooling sodium gas to within 0.5 billionth of a degree above absolute zero, at just 500 picokelvin. That's a temperature so precise, it's like measuring the distance between New York and Los Angeles down to the width of a single human hair. To achieve this, they used laser beams and magnetic fields to slow atoms to a near standstill, effectively hitting pause on their frantic thermal dance. This isn't just about bragging rights, it's a doorway to quantum strangeness. At these frigid extremes, atoms lose their individuality and merge into a bizarre new state of matter called a Bose-Einstein condensate. Picture thousands of atoms moving in perfect sync, like a school of fish suddenly becoming one superfluid droplet. Here, quantum effects normally hidden at everyday scales become impossible to ignore. Light slows to a crawl, fluids flow without friction, and matter behaves more like waves than particles. What's truly mind-bending? This ultra-cold playground lets scientists simulate conditions near black holes or the early universe right on Earth. By tweaking magnetic fields, they can make atoms repel or attract on command, mimicking cosmic phenomena impossible to study otherwise. It's a reminder that sometimes, to unlock the universe's grandest secrets, we need to start by bringing things to a whisper. Out in the vast stretches between stars and galaxies, space isn't just cold, it's a natural freezer operating at a staggering -270 degrees Celsius on average. That's just 3 degrees above absolute zero, the theoretical limit where all motion stops. But here's the twist: certain regions dip even lower. thanks to quirks in quantum physics that let heat escape more efficiently than expected. Picture the void not as a uniform chill, but as a cosmic freezer with uneven shelves, some spots hovering near the baseline, others plunging into deeper frost. The reason behind this icy emptiness is simple. Space lacks the molecules needed to trap and conduct heat. On Earth, warmth travels through air or water, but in the vacuum between celestial bodies, there's almost nothing to carry energy. Radiation from distant stars does little to temper the cold, like trying to heat a stadium with a single candle. Even sunlight, fierce enough to scorch Mercury, becomes a faint whisper over interstellar distances. Yet some of the coldest pockets defy conventional logic. Quantum mechanics allows particles in certain configurations to shed energy more completely, creating microscopic zones where temperatures flirt with those final few fractions of a degree above absolute zero. It's a reminder that even in the absence of matter, the universe finds ways to surprise us. The next time you gaze at the night sky, remember, what looks like serene darkness is actually a realm of extremes where nature's freezer runs colder than anything we could engineer on Earth. Venus stands as a terrifying warning of what happens when a planet's climate spirals out of control. Its thick, toxic atmosphere packed with carbon dioxide traps heat so efficiently that surface temperatures stay locked at a blistering 465 degrees Celsius year-round. That's hot enough to melt lead, yet what's truly shocking is how Venus got this way. Billions of years ago, scientists believe it may have had oceans and a more temperate climate. But as volcanic activity pumped more CO2 into the air, the greenhouse effect kicked into overdrive. Sunlight penetrated the atmosphere, heated the surface, and instead of escaping back into space, that warmth got trapped under a suffocating blanket of gas. The oceans boiled away, and the planet entered a feedback loop from which it never recovered. Here's where things get unsettling. Earth's atmosphere contains only a fraction of Venus' CO2, yet we're following a similar trajectory, just slower. Human activity has increased carbon dioxide levels by nearly 50% since the Industrial Revolution, and while we're nowhere near Venus extremes, the principle remains the same. Trapped heat alters weather patterns, melts ice caps, and raises sea levels. Venus teaches us that once a greenhouse effect tips past a critical point, reversing it becomes nearly impossible. The key difference: Venus had no one to intervene. We still have time to change course by cutting emissions, investing in renewable energy, and protecting natural CO2 absorbers like forests and oceans. The universe has handed us a cautionary tale written in scalding winds and acid clouds. The question is, will we learn from it before our own climate story takes a darker turn? Death Valley might hold the official record for Earth's hottest air temperature at a scorching 56.7 degrees Celsius, but the title of hottest place on the planet actually belongs to a far more extreme contender, Iran's Lut Desert. Satellite measurements have repeatedly clocked its sun-baked terrain at over 80 degrees Celsius, a heat so intense it could fry an egg on contact with the rocks. The difference: Death Valley's record comes from ground-level thermometers in shaded air, while the Lut's mind melting readings are taken from space, capturing the desert's surface as it absorbs and radiates solar fury. This vast salt plain doesn't just break records, it obliterates them. Towering sand dunes, some reaching 500 meters high, act like natural ovens, trapping heat under a cloudless sky. The landscape is so hostile that even bacteria struggle to survive, earning the Lut the nickname, the land where nothing casts a shadow. Yet despite its lifeless reputation, this desert holds secrets. Wind-carved ridges called yardangs stretch for miles, sculpted by ancient gusts into surreal, wave-like formations. Here's the twist: while Death Valley's heat lingers in the air, the Lut's surface burns like a stovetop, cooling dramatically at night. It's a reminder that temperature isn't just about numbers, it's about how heat behaves in different environments. One's a slow-cooked oven, the other is a blowtorch pointed directly at the ground. Both, however, stand as stark warnings of what our warming planet could increasingly resemble if extreme becomes the new normal. Beneath our planet's oceans, hidden in perpetual darkness, lies one of Earth's most extreme environments, hydrothermal vents spewing superheated water at a staggering 400 degrees Celsius. These towering black smokers erupt from cracks in the seafloor like underwater volcanoes, their jet-black plumes loaded with minerals that would be toxic to most life. Yet against all odds, these scalding depths teem with creatures straight out of science fiction. Giant tube worms with crimson plumes, ghostly white crabs, and bacteria that thrive on sulfur instead of sunlight. What makes these vents revolutionary isn't just their heat, it's how they've rewritten the rules of biology. The organisms here don't rely on photosynthesis or oxygen. They survive through chemosynthesis, converting volcanic chemicals into energy in a process that might mirror life's earliest origins. Some scientists believe these vents could be the cradle where Earth's first life forms emerged billions of years ago, sheltered from the violent surface by miles of protective ocean. The discovery of DNA-like molecules forming near vent-like conditions in labs adds weight to this theory, suggesting life might not need a gentle start, just the right kind of chaos. Even more mind-blowing, these ecosystems operate entirely in isolation. While sunlight drives nearly every food web on land, vent communities flourish in complete darkness, connected not to our world but to the planet's molten heart. If life can thrive under such alien conditions, it raises a tantalizing question. Could similar vents on icy moons like Europa or Enceladus harbor their own undiscovered creatures? Every expedition to these deep-sea infernos brings us closer to understanding not just our own origins, but the potential for life in the universe's most unforgiving corners. The vents challenge everything we thought we knew about survival, proving that where there's energy, even in the form of scorching, mineral-laden water, life finds a way. And if that's true on Earth, why not elsewhere? In the heart of a raging thunderstorm, nature unleashes a force so powerful it defies belief. A single bolt of lightning can reach an astonishing 30,000 degrees Celsius in a fraction of a second. That's 5 times hotter than the surface of the sun, concentrated into a jagged streak no wider than a few centimeters. This isn't just static electricity, it's a superheated explosion of plasma, hotter than lava, welding, or even the exhaust of a rocket at liftoff. The moment lightning strikes, it superheats the surrounding air so violently that it expands faster than the speed of sound, creating a shockwave we hear as thunder. That deafening crack isn't just noise, it's the sound of air molecules being torn apart and slammed back together by raw energy. But here's a twist that bends reality even further. While the sun's surface simmers at a mere 5,500 degrees, its heat is spread across a colossal sphere. Lightning, on the other hand, crams that extreme temperature into a fleeting channel thinner than a tree branch. And the results are terrifyingly precise: sand fused into glass, metal vaporized instantly, and trees split open as their sap boils into steam. Scientists call this phenomenon fulgurites, the ghostly sculptures left behind when lightning vaporizes soil into hollow tubes of melted quartz. Of course, with great heat comes spectacular side effects. Thunder isn't just one sound, it's a symphony of echoes. The initial deafening crack comes from the part of the bolt closest to you, while the rolling booms are distant segments of the lightning's path, each heating air at slightly different times. That's why you'll sometimes hear thunder as a long, rumbling growl, nature's way of reminding us that even the air we breathe isn't safe when the skies decide to turn up the heat. Perhaps most astonishing of all, lightning doesn't just happen on Earth. Venus's acid clouds crackle with discharges, Jupiter's storms spawn bolts 1,000 times more powerful than ours, and even Saturn's rings spark with electrical tantrums. But for now, Earth's lightning remains the most personal and the most lethal. A single strike carries enough energy to power a home for weeks, yet lasts less than a blink of an eye. It's a brutal reminder that even in our own atmosphere, the universe keeps temperatures dialed to extremes we're only beginning to understand. When humanity unlocked the power of the atom, we didn't just create a weapon, we briefly harnessed temperatures rivaling the cores of stars. During nuclear detonations, the fireball's heart soars to 100 million degrees Celsius, a fleeting echo of the universe's most violent stellar processes. For comparison, that's nearly 10 times hotter than the Sun's core, concentrated into a sphere of plasma no larger than a city block. The initial microseconds of a nuclear explosion compress atoms with such force that they fuse, releasing energy through the same process that lights up stars. Only here, it unfolds in a catastrophic instant rather than over billions of years. Historical footage of these tests reveals something surreal. The fireball's surface roils with the same convective patterns found on the Sun, a haunting reminder of the cosmic forces we've learned to replicate. As the blast expands, it generates X-rays so intense they ionize the surrounding air, creating a secondary pulse of thermal radiation. This isn't just heat, it's raw stellar fury bottled into a human-made event, scorching everything in its path to vapor before the shockwave even arrives. Yet there's a twisted irony here. While stars sustain their heat through steady fusion, balancing gravity's crush with radiant pressure, our bombs achieve similar temperatures through uncontrolled annihilation. The Tsar Bomba, humanity's most powerful detonation, briefly outshone the Sun in terms of raw energy output, its fireball visible from nearly 1,000 kilometers away. Scientists studying these explosions quickly noticed eerie parallels: the same plasma instabilities, the same magnetic field generation, even similar patterns of radioactive fallout drifting like interstellar dust. What does this tell us? That the universe's extremes aren't exclusive to distant galaxies or ancient supernova. They exist in the physics we've mastered here on Earth, for better or worse. While stars burn for eons, their power quietly shaping galaxies, our nuclear fires last mere seconds. Yet both share a common truth: when matter is pushed to its limits, the line between creation and destruction blurs into something both beautiful and terrifying. Deep within a nondescript facility in New Mexico, scientists have created something hotter than the heart of our Sun, using a machine that looks like it's straight out of a sci-fi movie. The Z machine, a towering apparatus with enough voltage to power a small city, has generated plasmas reaching a staggering 2 billion degrees Celsius, briefly hotter than the cores of most stars. Unlike nuclear weapons, which unleash their heat destructively, this device compresses tiny fuel capsules with magnetic fields so intense they mimic conditions inside fusion reactors. The result, a miniature star flickering to life for just billionths of a second, but offering a glimpse of the universe's most extreme energy potential. What's revolutionary here isn't just the temperature, it's the purpose. This isn't about breaking records, it's about harnessing the same process that powers stars to solve Earth's energy crisis. Fusion, the collision of hydrogen atoms into helium, could provide nearly limitless clean energy if we can control it. The Z machine's fleeting infernos help researchers understand how plasma behaves under star-like pressures, tackling hurdles like containing superheated material without it touching and vaporizing any physical walls. Yet the real magic lies in the details. To achieve these temperatures, the machine fires 20 million amps of electricity into a tungsten wire array thinner than a human hair. The wires vaporize instantly, creating a magnetic field that crushes the fuel at millions of kilometers per hour. For context, that's like squeezing Mount Everest down to the size of a sugar cube in less time than it takes to blink. While the Sun leisurely fuses atoms over billions of years, the Z machine does it in nanoseconds, a testament to human ingenuity bending cosmic forces to our will. The promise, a future where reactors replicate these conditions sustainably, producing energy without greenhouse gases or long-lived radioactive waste. Projects like ITER and Spark are already building on these experiments, inching closer to a breakthrough that could redefine civilization. Every pulse of the Z machine isn't just science, it's hope, written in temperatures hotter than anything in our solar system. If neutron stars are the universe's grim reapers, then pulsar wind nebulae are their ghostly shrouds expanding clouds of supercharged particles heated to a staggering 10 million degrees Celsius. These cosmic cauldrons form when a pulsar's furious magnetic field slingshots particles at near light speed, creating shockwaves that glow across the X-ray spectrum. The Crab Nebula, perhaps the most famous of these, pulses with the energy of a stellar corpse spinning 30 times per second, its tendrils of plasma stretching light years into space. Chandra's X-ray vision reveals an intricate latticework of energized gas, shimmering like a cosmic spiderweb forged in the aftermath of a supernova. What makes these nebulae so mesmerizing isn't just their heat, it's their precision. The pulsar at the heart of the Crab doesn't just spew chaos, it sculpts its surroundings with jets that erupt from its poles like celestial blowtorches, channeling particles into symmetrical arcs. These structures aren't static, they ripple outward at 5 million kilometers per hour, a slow-motion explosion frozen in time since the year 1054, when astronomers on Earth first recorded the supernova that birthed it. Yet beyond their beauty, these nebulae are cosmic power stations. The particles racing through them generate gamma rays, radio waves, and even antimatter, offering physicists a natural laboratory to study extreme physics. Every flicker of the Crab's pulsar injects fresh energy into the nebula, keeping it glowing brighter than 30,000 suns. It's a reminder that death in the universe isn't an end, it's a transformation, where the remains of a star become the fuel for new celestial spectacles. The death of a star doesn't always end with fireworks sometimes. It fades into the cosmos with quiet, unrelenting patience. White dwarfs, the glowing cores left behind when stars like our Sun exhaust their fuel, begin their afterlife as searing hot embers, shining at over 100,000 degrees Celsius. But unlike their violent supernova cousins, these stellar remnants don't explode or collapse. Instead, they embark on the universe's slowest cool-down, radiating away their heat one excruciating degree at a time across trillions of years. Picture a cosmic cinder the size of Earth, yet packing half the mass of our Sun, so dense that a single teaspoon would weigh as much as an elephant. Only the pressure of electrons, squeezed shoulder to shoulder, keeps it from collapsing further. But with no nuclear reactions left to sustain it, the white dwarf's brilliance is borrowed time. Initially, it outshines the full moon in sheer luminosity, but over millennia, it dims from blinding white to dull red, like a forgotten stove burner cooling after use. Here's what's wild: the universe isn't old enough for even the first white dwarfs to have fully faded. The coolest ones we've found still hover around 4,000 degrees Celsius, nowhere near the final stage. Eventually, they'll become black dwarfs, cold, dark husks invisible against the void. But that endpoint remains theoretical, a fate that won't unfold for another 10 trillion years at least. Until then, these dying stars serve as cosmic hourglasses, their fading light a countdown to a future so distant, even galaxies may not survive to witness it. Yet in their silence, white dwarfs hold secrets. Their atmospheres, often polluted by traces of heavier elements, are cosmic crime scenes, evidence of planets or asteroids that wandered too close and were shredded by unimaginable gravity. Others pulse with eerie regularity, their brightness flickering like lighthouse beacons as seismic waves ripple through their ultra-dense interiors. Each one is a tombstone inscribed with the story of its star's life, and a reminder that even in the cold depths of space, nothing truly vanishes without a trace. While most stars follow predictable orbits around galactic centers, some defy the rules entirely, hurtling through space at breakneck speeds like interstellar cannonballs. Take S5 HVS1, a hypervelocity star racing through the Milky Way at over 6 million kilometers per hour. its surface scorching at 20,000 degrees Celsius. This isn't just another hot star, it's a cosmic fugitive, ejected from its home by forces we're only beginning to understand. Scientists trace its path back to the heart of our galaxy, where the supermassive black hole likely slingshotted it outward in a gravitational showdown. Picture this: two stars orbiting each other get too close to the black hole's event horizon. One gets captured while the other is flung away at unimaginable speeds, heated by the sheer violence of its escape. Telescopes caught S5 HVS1 mid-flight, its ultraviolet glow betraying the extreme temperatures as it plows through interstellar gas, leaving a faint shockwave in its wake. What makes these rogue stars so fascinating isn't just their speed, it's their resilience. Despite the brutal ejection, they don't disintegrate. Instead, they streak across the cosmos like blazing messengers, carrying clues about the environments that spawn them. Simulations suggest S5 HVS1 will eventually escape the Milky Way entirely, destined to drift alone in the abyss between galaxies. Imagine the view from its surface, a once familiar night sky of stars fading into darkness as it leaves everything behind. Yet even in isolation, it burns defiantly, a testament to the universe's ability to turn chaos into something breathtaking. Each hypervelocity star we discover rewrites our understanding of galactic dynamics, proving that sometimes the most extreme temperatures come with the wildest journeys. While most stars shine with predictable stability, WR102 burns with a reckless intensity that puts even the fiercest stellar furnaces to shame. This Wolf-Rayet star clocks in at a blistering 210,000 degrees Celsius, so hot that it glows primarily in ultraviolet light, invisible to our eyes but revealing its true fury through specialized telescopes. Packed into this cosmic blowtorch is a star 20 times more massive than our Sun, burning through its fuel at a breakneck pace and shedding entire solar masses worth of material in violent stellar winds. Imagine winds so powerful they could strip a planet's atmosphere clean off in seconds, racing outward at nearly 3,000 kilometers per second. That's 6 million miles per hour, fast enough to cross the continental United States in less than a second. These aren't gentle breezes, they're supersonic tsunamis of ionized gas, tearing the star apart even before its inevitable supernova. With every passing millennium, WR102 loses enough material to build another Jupiter, shrouding itself in a glowing nebula of its own wreckage. What makes this star truly extraordinary isn't just its heat, it's the ticking clock at its core. Wolf-Rayet stars like this one are cosmic time bombs, fated to explode in a supernova within the next few 100,000 years. By cosmic standards, that's tomorrow. When it finally detonates, it won't just fade away, it'll unleash a gamma-ray burst, one of the universe's most destructive forces, capable of sterilizing entire star systems with its radiative fury. Yet even in its death throes, WR102 serves a purpose. The heavy elements forged in its core, carbon, oxygen, neon, will be blasted into space, seeding future generations of stars and planets. Telescopes like Hubble and James Webb study its turbulent winds, decoding clues about how such extreme stars reshape their surroundings. It's a reminder that in the cosmos, even destruction has meaning, and the hottest fires often light the way for what comes next. At the very heart of our Milky Way, a cosmic maelstrom rages in silence, hidden from human eyes by thick curtains of dust, but revealed in scorching detail through X-ray telescopes. Here, just 26,000 light-years away, the supermassive black hole Sagittarius isn't dining alone. It's surrounded by a searing ballet of stars and gas, all trapped in a gravitational waltz where temperatures routinely soar past several million degrees. Picture a region so densely packed that stars orbit at thousands of kilometers per second, their collisions and near misses superheating the surrounding gas into a churning plasma. This isn't just space weather. It's space inferno where magnetic fields twist into colossal loops, launching particles to energies that dwarf anything produced in Earth's particle accelerators. Infrared images cut through the dust to reveal hundreds of massive stars crammed into a space smaller than our solar system, their ferocious winds colliding like interstellar hurricanes. The real drama unfolds in the X-ray spectrum. Chandra's observations expose vast bubbles of million-degree gas expanding outward, remnants of past outbursts from Sagittarius itself. Somewhere in this chaos, clouds of molecular gas, raw material for new stars, get shredded and reheated before they can even coalesce. It's a celestial pressure cooker where only the toughest survive, and even they emerge forever changed. What makes this galactic core so extraordinary isn't just the heat, it's the paradox. Despite the violence, this region also births stars at a frantic pace, as if the universe insists on creating beauty amid the bedlam. Every flare of X-rays, every distorted orbit, tells a story of forces beyond human scale, a reminder that the Milky Way's serene spiral arms are just the calm exterior of a far fiercer beast. One of the Sun's greatest contradictions lies just above its surface, a blazing halo called the corona that burns at a baffling 1 million degrees Celsius, while the star's visible surface simmers at a relatively mild 5,500. This temperature inversion defies basic logic, like walking away from a campfire and getting scorched instead of cooler. The mystery only deepens when you realize the corona extends millions of kilometers into space, shimmering during solar eclipses like a ghostly, superheated veil. Scientists suspect the Sun's tangled magnetic fields act as hidden highways for energy. Loops of plasma constrained by these invisible lines whip and snap like cosmic rubber bands, transferring heat through waves and explosive reconnections. Some theories suggest nanoflares, countless tiny eruptions too small to detect individually, could be collectively roasting the corona. Others point to plasma turbulence, where charged particles collide in chaotic dances, transforming magnetic energy into blistering heat. What's wild is how this discovery reshapes our view of stars. If our own Sun, the most studied star in the universe, still hides such puzzles, imagine the secrets others might hold. Probes like Parker Solar Probe brave temperatures that would vaporize steel to skim the corona's edge, gathering clues. Each dataset reveals new twists, proving sometimes the most familiar objects hold the greatest surprises. The corona isn't just a scientific enigma, it's a reminder that even in well-trodden cosmic neighborhoods, nature keeps a few cards hidden up its sleeve. Understanding this solar riddle could unlock secrets about stellar winds, space weather, and even the behavior of distant exoplanets orbiting temperamental stars. For now, the corona remains a paradox wrapped in plasma, daring us to look closer. As our spacecraft plunge back to Earth from the icy void of space, they face one of the most violent temperature spikes in human engineering, a blistering 1,650 degrees Celsius generated by the sheer friction of re-entry. This isn't just heat, it's a firestorm of superheated plasma wrapping around the hull like a molten glove, glowing white-hot as it absorbs the kinetic energy of a vehicle screaming through the atmosphere at 25 times the speed of sound. The secret to survival lies in the shields, layers of ablative material designed to char and vaporize strategically, carrying heat away as they sacrifice themselves. NASA Apollo capsules used phenolic resin that slowly burned like a cosmic candle, while SpaceX's modern Dragon spacecraft rely on heat-resistant Pica-X tiles, a high-tech upgrade capable of multiple missions. Watching re-entry footage, you'll notice an eerie orange halo around the vehicle, not fire, but ionized air molecules ripped apart by the shockwave. What's truly astonishing isn't just the temperature, it's the gradient. While the plasma outside could melt steel, astronauts inside might need a light jacket, thanks to insulation that keeps the cabin as cozy as an air-conditioned room. The difference between a toasty 21 degrees Celsius inside and the inferno outside is thinner than a pizza oven's walls, a testament to human ingenuity bending physics to its will. This precise dance with plasma isn't just about returning home, it's a universal challenge. Every world with an atmosphere, from Mars to Venus, demands its own thermal solution. Future missions to Titan or gas giants will push materials even further, proving that when it comes to space travel, mastering extremes isn't optional, it's the only way back. Molten rock might seem like the ultimate symbol of heat, but not all of it burns equally. Take Hawaii's Kilauea, one of Earth's most active volcanoes. Its lava rivers glow at a scorching 1,200 degrees Celsius as they spill across the surface. That's hot enough to melt steel in seconds, yet it's practically cool compared to the hidden inferno lurking just beneath. Deeper underground, where pressure builds and gases dissolve, magma simmers at temperatures up to 400 degrees hotter, sometimes exceeding 1,600 degrees. The difference between lava and magma isn't just about location, it's a story of transformation. Once magma breaches the surface, escaping gases and exposure to air drop its temperature dramatically, turning it into the slower-moving lava we see. But down in the magma chamber, that molten rock retains its full fury, churning with the consistency of thick batter and carrying minerals that won't survive the journey upward. Kilauea's eruptions offer a rare glimpse into both worlds, fountains of orange lava bursting into the open while, miles below, magma reshapes the island from within. Scientists study this thermal divide to predict eruptions, since magma's behavior underground directly influences how violently or peacefully lava eventually flows. A subtle rise in magma temperature might signal increased pressure, hinting at an impending explosion. Meanwhile, the lava fields themselves become natural laboratories, revealing how Earth's crust rebuilds itself one searing layer at a time. Next time you see footage of glowing rivers swallowing roads, remember, you're only seeing half the heat. The real power lies buried where rock stays molten enough to reshape continents. Deep beneath our feet, Earth's inner core burns at an astonishing 5,700 degrees Celsius hotter than the surface of the Sun. Yet unlike the Sun's roiling plasma, this iron-nickel behemoth remains solid, squeezed into submission by pressures 3.5 million times greater than what we experience at sea level. Picture a celestial anvil where unfathomable weight overrides the chaos of heat, forcing atoms into a tightly packed lattice despite temperatures that should liquefy them instantly. The Sun's surface, by comparison, simmers at a cooler 5,500 degrees, its gases free to churn and flare without restraint. But Earth's core is a prisoner of its own gravity, its iron heart beating steadily beneath continents and oceans. This paradoxical state, solid yet scorching, powers our planet's magnetic field, a protective shield woven from the core's slow, rhythmic crystallization. Every few decades, that crystallization speeds up or slows down, subtly altering the length of our days by milliseconds. What's truly humbling, the core's heat isn't just leftovers from Earth's molten birth. Radioactive decay of elements like uranium and thorium provides a steady drip of energy, like a cosmic battery that's been running for 4.5 billion years. Meanwhile, the Sun's energy comes from fusion, smashing hydrogen atoms together under crushing gravity. Two extremes, two different blueprints for survival, one a raging fireball in the sky, the other a silent forge buried in darkness. Scientists study this blazing inner realm by listening to seismic waves as they ricochet through the planet, decoding their twists and delays like sonar pings in a labyrinth. Each tremor reveals another clue about the core's secrets: how it rotates slightly faster than the rest of Earth, how its western and eastern halves might behave differently. It's a reminder that even our own world, seemingly mapped and measured, still holds mysteries hotter than the stars. Imagine a storm where the raindrops aren't made of water, but diamonds. On ice giants like Uranus and Neptune, crushing pressures and scorching 5,000-degree interiors turn methane into glittering crystals that fall like cosmic hail. These planets may look serene from afar, but beneath their blue-hued atmospheres lies an alchemist's dream. Carbon atoms squeezed so violently they crystallize into solid diamond before plummeting toward the core. Scientists recreated these extreme conditions in labs, firing powerful lasers at plastic to simulate the methane-rich environments of these distant worlds. In mere nanoseconds, the carbon atoms rearranged into diamond structures, proof that nature's most coveted gems might be as common as sand in certain corners of the solar system. Unlike Earth's diamonds, forged over billions of years deep underground, these extraterrestrial jewels form continuously in the turbulent layers of ice giants, sinking until they potentially pool into literal diamond oceans near the core. What's even wilder, the friction of diamonds rubbing together in these high-pressure zones might generate enough heat to influence the planet's magnetic fields, adding a sparkling twist to how we understand their internal dynamics. Next time you gaze at Neptune's serene blue glow, remember, it's not just a planet, it's a jewelry factory operating at scales beyond human greed, where storms of priceless gems rage unseen beneath the clouds. While we'll never mine these diamond downpours, their existence reshapes our understanding of planetary interiors, proving that even the most familiar elements can behave in extraordinary ways when subjected to the universe's extremes. Forget the sun's core or even supernova. Humanity has briefly unlocked temperatures that make them seem lukewarm. Inside CERN colossal particle colliders, scientists have recreated a fleeting state of matter so blistering it defies comprehension. Quark-gluon plasma heated to 5.5 trillion degrees Celsius. That's over 300,000 times hotter than the heart of our sun. A seething primordial soup where protons and neutrons melt into their most fundamental building blocks. This isn't just about breaking records, it's a time machine to the universe's first microseconds, when heavy ions like gold or lead smash together at near light speed. They compress so violently that they mimic conditions from the Big Bang itself. For less than a trillionth of a second, quarks and gluons particles, normally glued tight inside atoms, roam freely like they haven't since the cosmos was smaller than a peach. Detectors like Alice capture this ephemeral fireball, revealing how the universe might have behaved before even atoms existed. The real magic lies in the aftermath. As this plasma cools, quarks and gluons snap back together like cosmic Lego, forming new particles in a process that mirrors how the early universe assembled itself. These experiments aren't just recreating history, they're testing the very rules that govern how matter behaves under extremes no star or black hole could naturally produce. Every collision is a miniature genesis, a fleeting window into a time when heat ruled the cosmos so completely, even the laws we take for granted were still being written. What's humbling, this 5.5 trillion degree inferno exists only in a space narrower than an atom's nucleus, sustained for less time than it takes light to cross one. Yet in that microscopic flash, we've touched temperatures unseen for 13.8 billion years, proof that sometimes to uncover the universe's greatest secrets, we need to turn up the heat beyond even nature's limits. Far beyond our solar system, drifting through the perpetual night of interstellar space, lies a frozen world that makes Pluto seem almost tropical. Meet Ogle 2005 BLG 390 LB, an exiled super-Earth, locked in a deep freeze at -220 degrees Celsius, where even the hardiest Antarctic microbes would flash freeze in seconds. Discovered through a cosmic trick of gravity-bending starlight, this Earth-like planet orbits so far from its dim red dwarf star that a single year lasts a glacial 10 Earth decades. What makes this icy wanderer fascinating isn't just its cold, it's the haunting familiarity of its size. Roughly 5 times Earth's mass, it could have been a twin of our own world under different circumstances. Instead, its surface likely resembles Antarctica's dry valleys magnified to planetary scale. Endless plains of nitrogen and methane ice under a starry black sky, untouched by sunlight's warmth for billions of years. Telescopes can't yet glimpse its surface, but physics paints a stark picture. Any atmosphere would have long ago collapsed into frozen deposits, leaving behind a desert of frost under an eternally twilit sky. Yet the real intrigue lies in what Ogle 2005b G390lb represents. For every balmy exoplanet orbiting in a star's Goldilocks zone, there may be dozens of these frozen outcasts drifting in the outer dark. Some could harbor subsurface oceans like Europa, kept liquid by radioactive decay or tidal flexing. Others might be fossil worlds preserving snapshots of early planetary chemistry in their icy crusts. While this particular super-Earth is too harsh for life as we know it, its existence expands the map of where and how planets can form. In the grand catalogue of exoplanets, Ogle 2005b G390lb stands as a reminder that Earth's cozy climate is the exception, not the rule. Most of the universe's real estate leans toward extremes, with frozen frontiers far outnumbering temperate havens. As we keep searching the cosmos for neighbors, we do well to remember, not all Earth-sized worlds are Earth-like. Some wear their ice like a crown, orbiting in silent majesty where the cold is king. East Antarctica holds the record for the most bone-chilling temperature ever measured on Earth, a staggering -93.2 degrees Celsius, captured by satellite in the heart of winter. That's colder than dry ice, colder than Mars on a mild day, and just a whisper away from the lowest temperatures ever recorded on our planet's surface. At these extremes, the air itself feels like shattered glass, and exposed skin can freeze in under 2 minutes. Yet every year, brave researchers venture into this frozen desert, armed with survival strategies that sound like something out of a sci-fi novel. First rule: never breathe unprotected. Inhaling air that cold can damage lungs instantly, so scientists use specially heated breathing masks. Their insulated boots are thick enough to walk on boiling lava, yet they still risk frostbite if they pause too long in one spot. Clothing becomes a meticulously engineered system, layer upon layer of advanced fabrics, with no skin left uncovered. Even eyelashes aren't safe. Moisture from blinking can freeze eyelids shut without constant movement. The research stations here, like Russia's Vostok station, are lifelines in the void. Double-walled structures house crews through months of perpetual darkness, where steel becomes brittle as uncooked pasta and fuel turns to gel. Yet the rewards outweigh the risks. This icy wasteland preserves Earth's purest climate records in its mile thick glaciers, offering clues about our planet's past and future. Every ice core drilled here is a time capsule, trapping ancient air bubbles that reveal how Earth's atmosphere has changed over millennia. What's truly remarkable? Life still finds a way. Microbes thrive beneath the ice in subglacial lakes, while extremophile bacteria cling to existence in the dry valleys, surviving on trace chemicals in the rock. Antarctica's cold might be brutal, but it's also a laboratory for resilience, proving that even in the harshest corners of our world, nature refuses to surrender. While much of humanity basks in mild climates, one remote Siberian village thrives where most wouldn't last an hour. Oymyakon, Russia. Here, winter isn't just a season. It's a merciless force that plunges temperatures to -71.2 degrees Celsius, the coldest ever recorded in an inhabited place. Cars run non-stop to prevent fuel from freezing solid, while schoolchildren bundle up for class only if it's warmer than -52. The air is so frigid that exhaled breath crystallizes instantly, shimmering like diamond dust before hitting the ground. Survival here demands ingenuity. Pipes can't be buried underground because the permafrost never thaws, so toilets are often outhouses perched over exposed trenches. Eyeglasses freeze to faces and ink in pens solidifies mid-sentence. Yet the 500 residents of Oymyakon aren't just enduring, they've adapted. Local diets feature hearty staples like frozen raw fish, reindeer meat, and steaming bowls of stroganina, a traditional dish of shaved ice fish eaten like carpaccio. Even the cows wear custom-made felt coats to survive the winter pastures. The cold shapes every ritual. Funeral processions stretch for days as digging graves requires thawing the ground with bonfires. Yet despite the hardships, community bonds run deep. Saunas or banyas become lifelines, their blistering heat offering fleeting relief. Tourists brave enough to visit leave with certificates proclaiming their survival, while scientists study the villagers' resilience, from their unique metabolism to the way their speech patterns adapt to conserve breath in sub-zero winds. Oymyakon's extremes aren't just a curiosity, they're a testament to human adaptability. In a world where we control our environments with thermostats and insulation, this village stands as a reminder that life, against all odds, finds a way to flourish. And when summer finally arrives, temperatures soar to a balmy 30 degrees, turning the land of eternal frost into a fleeting green paradise until winter's grip tightens once more. But just as absolute zero marks the coldest possible limit, the universe has an opposite extreme, a theoretical ceiling called the Planck temperature. At a mind-numbing 1.4 times 10 to the 32 degrees Celsius, this is the upper boundary where the very laws of physics dissolve into chaos. To put that incomprehensible number into perspective, it's a million billion times hotter than the core of a supernova. At this point, particles move with such insane energy that gravity, electromagnetism, and even the strong nuclear force cease to function as we know them. Quantum fluctuations would rip spacetime itself apart, making concepts like heat or matter meaningless, the only time the universe is believed to have reached this extreme. The first instant of the Big Bang, when all existence was compressed into a singularity smaller than a single atom. For a fraction of a Planck time, the smallest measurable moment, everything we understand about reality was rewritten in that searing forge. What's wild is that this isn't just abstract math. The Planck temperature is a hard limit dictated by fundamental constants, like the speed of light and the strength of gravity woven into the fabric of the cosmos. While we'll never recreate such conditions, studying them helps physicists probe the origins of everything. It's a reminder that the universe, for all its fury, still plays by rules even when those rules lead us to the edge of imagination. Nature's most spectacular light shows don't just happen in the sky, sometimes they erupt from the ground. During volcanic eruptions, a phenomenon called volcanic lightning transforms plumes of ash into crackling storms hotter than the surface of the sun. When Chile's Calbuco volcano roared to life in 2015, cameras captured these surreal electrical bursts, forked bolts as wide as highways, superheated to a staggering 30,000 degrees Celsius. So how does a volcano already spewing molten rock also generate lightning? The secret lies in chaos. As ash particles rocket upward, they collide violently, stripping electrons off one another like a colossal static shock. These charged particles separate lighter ash carrying positive charges skyward, while heavier debris holds negative charges near the vent. The imbalance becomes so extreme that the air itself ionizes, forging conductive paths for electricity to rip through the ash cloud. The results are unlike any storm on Earth. Instead of rain, these bolts dance through swirling pyroclastic flows, illuminating entire valleys with their blue-white fury. Calbuco's eruption produced nearly 1,000 strikes in just 90 minutes, some arcing horizontally for miles. Scientists now study these discharges as natural laboratories, clues about how lightning might form on other worlds with volcanic activity, like Jupiter's moon Io or even ancient Mars. But volcanic lightning isn't just a scientific curiosity, it's a lifeline for monitoring eruptions. By tracking these electrical outbursts, researchers can gauge an eruption's intensity in real time, often before seismic sensors or satellites detect changes. Next time you see footage of an ash-lit sky split by lightning, remember, you're witnessing one of nature's rarest convergences of fire and electricity, where Earth's raw power writes its own rules. In the realm of extreme heat, one chemical stands unrivaled: dicyanocetylene, a compound capable of producing flames reaching an astonishing 4,990 degrees Celsius when burned in pure oxygen. That's hotter than the surface of most stars and nearly twice the temperature of lava erupting from Earth's fiercest volcanoes. While nature has its own scorching phenomena, this man-made inferno is harnessed for tasks where ordinary torches simply wouldn't cut it literally. Industrial facilities use this searing flame to slice through thick metals like warm butter, where precision and sheer thermal power are non-negotiable. The science behind this blistering burn lies in dicyanocetyllene's molecular structure. Its tightly bonded carbon and nitrogen atoms release colossal energy when they break apart and recombine with oxygen, unleashing a torrent of heat that outshines even acetylene, the traditional torch fuel. Watching it in action is like staring into a miniature sun, a focused beam of blue-white fury that vaporizes steel in seconds. Yet what's truly remarkable isn't just the temperature, it's the control. Engineers manipulate this extreme heat with surgical precision, guiding it through robotic arms or handheld rigs to craft everything from spacecraft components to nuclear reactor parts. In a cosmic twist, the same chemistry that fuels celestial firestorms now helps build humanity's most advanced machines. So next time you see a perfectly cut steel beam, remember, somewhere in the workshop, science has tamed a flame hotter than the stars. Mars isn't just the red planet, it's home to the largest volcano in the solar system, Olympus Mons, a towering giant with a fiery past that makes Earth's most explosive eruptions look tame. This ancient behemoth stretches nearly 22 kilometers high, almost 3 times the height of Mount Everest, and its slopes tell the story of lava flows that once roared at a staggering 1,500 degrees Celsius. Unlike Earth's volcanoes, which erupt and collapse over millions of years, Olympus Mons likely oozed molten rock for hundreds of millions of years straight, its lava so hot it could have vaporized iron on contact. What made these eruptions so extreme wasn't just the heat, it was the sheer volume. Without shifting tectonic plates to divert its output, Olympus Mons had no off switch. Lava pooled and spread in relentless sheets, building layer upon layer until the volcano became a planetary landmark visible from space. Recent satellite images reveal hardened rivers of basalt wider than entire cities, frozen in time like scars from Mars' volcanic heyday. But here's the twist, even at those blistering temperatures, Mars' thin atmosphere meant lava behaved differently than on Earth. Without dense air to slow its flow, it could have traveled hundreds of kilometers, sculpting vast plains in its wake. Some scientists speculate that underground magma chambers might still linger, dormant but not entirely dead. If Olympus Mons ever wakes again, it wouldn't just be an eruption, it'd be a planet-altering event. This colossal fire mountain doesn't just rewrite the rules of volcanology, it forces us to rethink how planetary landscapes evolve under extremes. While Earth's volcanoes rise and fall like fleeting candles, Olympus Mons stands as a monument to patience, a reminder that time and heat can build mountains taller than anything in our wildest dreams. The next time you gaze at Mars, remember, its quiet surface was once a canvas painted in liquid fire. High above Earth's polar skies, NASA satellites have spotted something unexpected: storm clouds so cold they defy atmospheric records. These swirling behemoths, lurking near the edge of space, plunge to a bone-chilling -111 degrees Celsius, colder than winter on Mars or even the dark side of the Moon. Scientists first detected these hyper-cold clouds using infrared sensors, revealing ice crystals forming at temperatures once thought impossible in our planet's atmosphere. So how does a cloud get this cold? The answer lies in the turbulent dance of winds at the boundary between the troposphere and stratosphere, where moisture gets sucked upward into towering storms. As air rises rapidly, it expands and cools, like opening a freezer door, only in this case, the freezer is the size of a continent. The result, supercooled water droplets that freeze into ice crystals almost instantly. creating clouds so frigid they shimmer like shattered glass against the blackness of space. What's truly astonishing is the scale. These aren't wispy cirrus clouds, they're monstrous systems spanning hundreds of kilometers, often forming over severe thunderstorms or tropical cyclones. Satellite images show their ghostly outlines glowing in thermal data, like frost spreading across a cosmic windowpane. Researchers suspect these extreme conditions might even influence how storms intensify below, acting as a high-altitude thermostat for Earth's weather systems. While these icy giants pose no direct threat to us on the ground, their discovery reshapes our understanding of atmospheric limits. Next time you gaze up at a stormy sky, remember, what happens below might just be the tip of the iceberg, literally. Because far above, where the air thins to near vacuum, nature is still busy rewriting the rulebook on cold. Even ghostly particles can burn with unimaginable fury. Deep beneath the Antarctic ice, the Ice Cube Neutrino Observatory recently caught something extraordinary, a neutrino blazing at a mind-melting 10 trillion degrees Celsius, flung across the cosmos from a monstrous blazar 5 billion light-years away. Neutrinos are usually the universe's shyest particles. Trillions pass through your body every second without a trace. But this one, it packed the energy of a major league fastball into a speck smaller than an atom, screaming through space at nearly light speed. The secret lies in its origin. A blazar, the supermassive black hole at the heart of a galaxy, devouring matter so violently it fires particle jets straight at Earth. When IceCube's sensors lit up in 2022, it wasn't just detecting a neutrino, it was catching a cosmic bullet fired from the most extreme particle accelerator in existence. What's wild is how we spotted it. IceCube's grid of frozen sensors waits patiently in the darkness, tracking the faint blue flashes when neutrinos rarely interact with the ice. This particular collision unleashed a particle shower so energetic, it outshone the detector's usual events by 1,000-fold. For a fleeting instant, the Antarctic ice became the universe's most unlikely thermometer, measuring a temperature hotter than anything in our solar system's history. Yet the real marvel isn't just the heat, it's the journey. This neutrino spent eons racing through voids and magnetic fields, dodging galaxies and black holes, only to meet its end in humanity's strangest lab. Its detection didn't just break records, it proved that the most extreme physics isn't confined to far-off stars. Sometimes it's buried right under our feet, waiting to be uncovered by those patient enough to listen to the ice. While Io's equator blazes with rivers of scorching lava, its poles tell a dramatically different story, a realm where sulfur dioxide gas freezes solid into vast white plains at a bone-chilling -150 degrees Celsius. This moon isn't just a world of fire and ice, it's both at once, with volcanic vents spewing molten rock near the equator while explosive geysers erupt near the poles, blasting plumes of frozen gas hundreds of kilometers into space. The secret lies in Io's wild temperature swings. Under Jupiter's relentless gravitational pull, the moon's interior churns with enough friction to melt rock, feeding its famous lava lakes. But at the poles, where sunlight barely grazes the surface, sulfur dioxide from volcanic outgassing condenses directly into frost, blanketing the terrain in an eerie, glittering crust. When this icy reservoir gets heated from below, whether by rising magma or shifting tides, it doesn't just melt. It explodes, creating geysers that launch frosty debris at nearly half the speed of sound. NASA Galileo spacecraft caught these polar outbursts in action, revealing a surreal landscape where plumes of frozen gas arc gracefully against the blackness of space, like cosmic snow machines gone rogue. Unlike Earth's water-based geysers, these jets are powered by vaporized sulfur dioxide, a compound that shifts straight from solid to gas in Io's thin atmosphere. The result, a spectacle where volcanic heat and cryogenic cold collide, proving that even in the extremes of our solar system, nature loves a good paradox. What's truly mind-bending? Some of this frost doesn't just fall back to the surface, it escapes Io entirely, feeding a vast donut-shaped cloud of ionized sulfur that orbits Jupiter itself. This delicate dance of freeze and fury reminds us that even the most violent worlds can harbor pockets of unexpected beauty, where fire and frost exist side by side in an endless celestial tug of war. Far out in the frigid reaches of a solar system, there's an invisible boundary that holds the secret to how planets form, the ice line. This astronomical threshold marks the exact distance from a star where temperatures drop low enough for water to freeze solid in space. Inside this line, worlds bake dry under the star's glare. Beyond it, ice becomes a cosmic construction material, gluing dust grains together into the building blocks of planets. Picture a young star still swaddled in its swirling disk of gas and dust. Close in, fierce heat vaporizes everything, leaving only hardy metals and silicates to clump together into rocky worlds like Earth and Mars. But cross the ice line, and suddenly water molecules can stick to each other, coating specks of dust with frosty shells. These icy particles collide gently instead of bouncing apart, growing faster and larger than their inner system cousins. Over time, they snowball into the massive cores of gas giants like Jupiter or the frozen realms of Uranus and Neptune. What's fascinating is how much power this simple shift in temperature wields. The ice line isn't static. It migrates inward as a star ages and cools, rewriting the planetary blueprints over millions of years. Some astronomers even suspect Earth's water arrived via icy asteroids flung inward after forming beyond our solar system's early ice line. Without that frosty frontier, worlds like ours might have stayed barren dust bowls, never gathering the oceans that make life possible. From scorching Mercury to the icy Kuiper belt, the ice line's legacy is etched across every planet, moon, and comet. It's proof that sometimes the universe's grandest designs hinge on something as simple as a drop in temperature, the moment a star's warmth fades just enough to let the frost take hold. Among nature's most terrifying spectacles are firewhirls, tornadoes of flame that spin with the fury of a wildfire and the precision of a cyclone. These towering vortices don't just burn, they devour, reaching temperatures of 1090 degrees Celsius, hot enough to melt aluminum and twist steel beams like taffy. Imagine a column of fire 30 stories tall, whipping embers and superheated air into a vortex so intense, it creates its own wind system, pulling in fresh oxygen to feed its insatiable hunger. The recipe for these infernal twisters requires just the right chaos, extreme heat, turbulent winds, and an abundance of fuel. During California's Car Fire in 2018, a firewhirl with winds rivaling a Category 3 hurricane tore through neighborhoods, hurling flaming debris kilometers ahead of the main blaze. Unlike ordinary wildfires that crawl or spread predictably, these spiraling monsters move with eerie purpose, leaving behind scorched spirals etched into the earth like signatures of destruction. What makes them even deadlier is their unpredictability. Firewhirls can form in seconds, changing direction without warning, and their intense heat radiates outward, igniting everything nearby long before the flames themselves arrive. Firefighters describe encountering them as facing a living force, one that breathes, grows, and twists the very rules of combustion. Satellite images from Australia's bushfires revealed multiple whirls dancing simultaneously across the landscape, each one a self-sustaining engine of devastation. Yet amid the terror, there's scientific fascination. Researchers study these phenomena to improve firefighting tactics, using fluid dynamics to predict their behavior. NASA even analyzes firewhirls to understand plasma vortices on the Sun, proving that sometimes Earth's most extreme forces mirror those of the cosmos itself. The next time you see smoke curling skyward, watch closely. Nature might just be spinning its deadliest masterpiece. After trillions of years of cosmic fireworks, stars burning, galaxies colliding, black holes feasting, the universe will face its quietest, coldest fate. Not with a bang, but with an endless, deepening freeze. Scientists call this the heat death scenario, where temperatures creep infinitely close to absolute zero across distances so vast, even time loses meaning. Picture a reality where all stars have flickered out, black holes evaporated, and every surviving atom drifts so far apart that the cosmos becomes a silent, near-perfect vacuum. Across timescales that make the age of our current universe seem like a blink-think one, followed by 100 zeros years, this profound chill sets in not as a dramatic event, but as the universe's final, irreversible whisper. Here's the chilling truth: it's not about a sudden freeze, but the slow, inevitable dispersal of energy. Stars exhaust their fuel, galaxies stop forming, and matter itself decays. Eventually, even protons, the building blocks of atoms, may disintegrate, leaving behind only scattered particles too feeble to interact. Quantum fluctuations might still spark tiny bursts of warmth, but these would be fleeting anomalies in an ocean of cold. The universe, once brimming with seething plasma and stellar nurseries, becomes a near-uniform graveyard where temperature differences, the very engine of change, vanish entirely. But there's a strange beauty in this bleak vision. The heat death isn't destruction, it's transformation on the grandest scale. Energy never disappears, it just becomes so diffuse that no work can be extracted from it, like ink dissolving in an infinite glass of water. Some theories even suggest that in this frozen twilight, quantum tunneling could birth new universes from the void, sparking cycles of rebirth we can scarcely imagine. For now, though, our vibrant, chaotic cosmos burns bright, a fleeting fire against the coming cold, reminding us that even the longest stories have an ending. And in that ending, the universe teaches its final lesson: all heat fades, but the journey there is what makes existence spectacular. From the 15 million degree inferno of the sun's core to the frozen whispers of the Boomerang Nebula, we've journeyed across a universe where temperature isn't just a number, it's the invisible force shaping stars, planets, and even the fabric of reality itself. These 50 extremes aren't just records, they're cosmic stories written in blistering plasma and diamond-hard ice, each one revealing how heat and cold sculpt everything from the birth of galaxies to the fate of atoms. Think about this: without these staggering temperatures, the gold in your jewelry wouldn't exist, the air you breathe wouldn't have formed, and life as we know it might never have sparked into being. From the trillion-degree echoes of the Big Bang to the sub-zero deserts of distant exoplanets, the universe thrives on contrast, pushing boundaries in ways that challenge our very understanding of physics. Now, we'd love to hear from you. Which of these extremes left you awestruck? Was it the diamond rain on Neptune, the solar tornadoes hotter than the sun itself, or something else entirely? Drop your favorites in the comments, and if there's a mind-bending cosmic phenomenon we should explore next, let us know. The universe is vast, and every discovery starts with curiosity. So keep looking up, keep questioning, and remember, whether it's a star's fiery heart or the silent chill of deep space, the cosmos always has another secret waiting to be uncovered. Until next time, stay stellar.